Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Today we will discuss heuristic searches. In last session, we have already discussed exhaustive searches. Exhaustive searches means uninformed searches, which means we doesn't have any information about the problem, how to solve. But here in heuristic searches, we'll have some heuristic value to solve the problem. From start state to goal state, there is some heuristic value. Based upon the heuristic value, we'll go to the towards the problem solving. So how to calculate a heuristic value? So here we'll use the famous methods called as Euclidean distance and Manhattan distance methods. So in these algorithms, already some imaginary or assumptionary values are there. So directly we'll start the techniques which are used to solve the problem. So let's see the overview of the presentation. Branch and bound search, hill climbing, beam search, and best first search. Let's see one by one. Branch and bound search. In the branch and bound search, there is a cost function. We already discussed, that is heuristic function or heuristic value will be there. Means prior information about the problem solving. There is some information towards to solve the problem. So in branch and bound search method, there is a cost function is designed that assigns a cumulative expenses to the path from start node to the current node. So it will start from start node, root node. So for example, there is a one value A, B, C, then this is the G, then it will be calculated S to A to G. The cumulative value from start node to the current node. Towards that, it will repeat the same procedure. For example, there is another level, is there. At last here it is the goal node. Then it will carry the cumulative cost function to the start node to the goal node. That is what the cumulative cost function will be carried. While generating search space, a least cost path obtained so far is expanded. For example, here it is a 3 and here it is a 5 and here it is a 2. Then it will carry this 2 value to reach the goal state. For example, there is no connection between these two. Then which one is the least one? It will take that least one and it will carry the goal state. Since this search expands the least cost partial path, it is sometimes also called as uniform cost search. Branch and bound is also called as uniform cost search algorithm. Okay, let's see the algorithm of branch and bound searches. Every algorithm contains the start and goal nodes, and local variables are open, closed, node, successors, and found. So the open, the list contains which are explode. It is not examined, just explode. Whatever nodes are explode, those will be placed into the open list. In the closed list, whatever examined means already visited, that nodes will be placed into the closed. And to pronounce the open list nodes will be taken as a node as a word. Next, successors. After exploring the first node or second node, whatever the nodes are there linked to that parent node, then that are called as a successors. This found is the Boolean value to calculate the output, yes or no. If the path is exist, then the output is yes. If path does not exist from start node to goal node, then it is no. Let's see the method. So here, initially the open list contain the start node and closed list contain the pi, means nothing. Okay, let's see the loop. Open is not empty and found is false. Found initially we have taken as a false. Whenever we compare with the start node with the goal node, if not only start node, the node will be compared with the goal node. If it is a match, then it assigned as found is assigned as a true, otherwise it will be false. So initially open is not empty, so open is already contained the start node, and found is false. Then remove the top element from the open list. Whatever element contain the open list, that will be removed. Call it as node. I already said here the node, to pronounce that we have taken node. as a word. If node is the goal node, the comparison, the current node is the goal node, then set found equal to true. Else add node to the closed list. So that is already examined. So add that start node into the closed list. Find successors of that node. So here A, B, C, whatever successors are there for the start node, we need to explore that successors, compute their G value. What is the cost function of that successors? Store them in the open list. Again, we need to store them into the open list according to the ascending order. Sort all the nodes in the open list based on their cost function values. For example, 5, 2, 1. Then C, B, A. Based upon the values, we need to sort. Again it will goes to the while loop and it will check the condition open is not empty and found equal to false. The procedure will repeat until it reaches the goal node. Next, how it will be calculated, how it will be tested. From a point of view, this method is as bad as the depth first and breadth first search. This can be improved by using a dynamic programming. Delete those parts which are redundant, duplicate, we need to remove those one. The possible solution is how to test. Start, generate a possible solution, test if it is a goal. If not, go to the start, else quit. This is the procedure how to reduce this one. Let's see the example. So here in this example, there are 4 nodes are there, 0, 1, 2, 3. 0 is the start state and 2 is the goal state. It will start from the start state. This is the open and this is the closed. So initially the open contains the start node 0. Okay. Then this 0 is called as the node. This 0 is compared with the goal node 2. It is not matched. Then it will be explored 0, 1, 3, 2. And it will find out the cost value. 1 is 10, 3 is 20, 2 is 15. Then these nodes will be sorted. This O will be moved to the closed. Now open is empty and the open contains 1, 2, 3. According to the G values will be sorted and whatever least value will be there, that will be explored now. 1 contains 3 and 2. Now again it will be calculated. So along with these values, here in this algorithm it will carry the cumulative cost. So along with these values, 1 will be moved to the closed and 3, 2 will be added here. The 3 already contain here in the open list 1, 2, 3. The 2 contains as a 15, 3 having the 20. Now again 3 and 2 will be added. 3. The 3 value is 10 plus 25. It will be carried the cumulative value 0 to 1, 1 to 3. So 10 plus 25 is 35. Again next the 2 will be added. 10 plus 35, this 10 and this 35 added together 45. Now 15, 20, 35, 45 will be carried next. So what is the next least value? 15. So these 2 will be compared. Now the current node is 2. 2 will be compared with the goal node. Yes, it is goal node. Then it will stop tracing and it will give the output. This is how the branch and bound algorithm will works. Let's see the next algorithm, that is hill climbing algorithm. So hill climbing algorithm will turn the depth first search as into a hill climbing. So here it is an optimization technique that belongs to the local search. So hill climbing contains the local information. It doesn't contain overall information about the problem to solve. Next, hill climbing can be used to solve problems that have many solutions, but where some solutions are better than others. So here, for example, if you take 8 puzzle problem, there is a 3 by 3 grid. So the 8 tiles are arranged in such a manner in the start state and the goal state. Okay, there is an empty cell. By using that empty cell, we need to reach the goal state. There are multiple solutions will be available. So whenever we are using hill climbing algorithm, we can reach this goal state. But in some scenarios, there are some other solutions also better than this hill climbing algorithm. That is what this point meaning. Next, let's see the algorithm. I said already input contains the start and goal states, local variables, open, node, successors and found. The output is if the path exists, yes, no, there is no path means no. So initially the open contains the start node and found is false. Open is not empty and found is false. Then remove the top element from the open list and assign it to node. Node is the goal, then set found equal to true. Then what is the difference between that branch and bound and hill climbing algorithm? In branch and bound, every time it will carry all the nodes which are available in the open list. But in the hill climbing algorithm, whatever top element will be removed from the open list, it will carry in such a manner, it won't go back, backtrack, whatever least values will be there to take those values. It will be taken as the top element. From this top element only it will go. From this point, if it is the start least value, then it will carry this one. For example, at this point, it contains here the less value is there. For example, compare to this and this one. For example, this one is A, this one is B. B is the smallest value comparing to A, but it won't go back. It will carry this one only. This is how hill climbing will work. That is the difference between branch and bound and hill climbing. But branch and bound, it will every time it will compare with all the nodes available in the open list. So if node is the goal, set found equal to true. Otherwise, find successors of node if any. Sort successors based on their estimated cost to the goal state. Add the sorted successors to front of the open list. It won't sort them comparing to the old values. It will sort the level by level and it will pick one of the best value in that level. And if found equal to true, return yes, otherwise no. So here hill climbing having some problems. Let's see the problems. So the first one is local maxima. This local maxima means if it is a state that is better than all its neighbors. Let's look at this diagram here. At this point, it is called as a local maxima. There is a far away, there is another one is there, but it won't go there. It will stick on here. If it will take a next move, then that is the worst move. That's why it will stick on here. So here, from this state, all moves look to be worse in such a situation. Backtrack to some earlier state and try going to in different direction to find a solution. This is the solution for local maxima. Backtrack and find the different way to reach the solution, means this point. So here in the hill climbing, it will go like this, and here it will says that this one is the optimal solution, but it is not the optimal solution. If you compare here there is another optimal solution is there, but it won't go there. So for that, the solution is backtrack to some earlier state and try going in different direction to find a solution. The local maximum means all neighbor states have the same value. It is a state that is better than all its neighbor states. This point is the better than its neighbor states. The second one is plateau or flat area. If you look this diagram, you can understand it. Look at this one. All these neighbors having the same values. So here it is a flat area of the search space where all neighboring states has the same value. It is not possible to determine the best direction. In such a situation, make a big jump to go to the direction to try to get the new value, new section of the search space. But in the hill climbing, it will take one of the value is the optimal solution. It won't go there. For that, this is the one of the solution. The third one is the ridge. Is another problem with hill climbing. Here, look at this. It is an area of search space that is higher than surrounding areas. So here, It is one of the local maxima only. So here traversed by single moves in any one direction. It is a special kind of local maxima. So here, to backtrack, apply two or more rules before doing the test moving in several directions at once. But it won't apply these rules in this hill climbing. But in this, there is a temporary solution says that we need to apply the two or more rules before doing the test. So ridge means it is a special kind of local maxima, and it is an area of search space that is higher than surrounding areas, but that can't be traversed by a single moves in any one direction. Okay, that is the hill climbing problem. The next one is beam search. The next algorithm is beam search algorithm. It is a heuristic algorithm which contains the W number of best nodes. In the branch and bound, our next algorithm best for search will take only one node. That node will be carried to the next, and to do such a process will move to the goal. But here in this beam search algorithm, there is a W number of best nodes at each level is always expanded. For example, as this is the start node, and this one is the first level, second level, third level. So the W is defined as a 3. So in this level, it will be identified 3 best nodes. The next level also 3 best nodes. Towards the goal state, every level it will take the 3 nodes. So beam search uses BFS to build a search tree. At each level of tree, it generates all its successors of the states at the current level, sorts them in the order of increasing heuristic values, and it will pick up the W number of states at each level. So here W means width of the beam search and B is the branching factor. There will only be W into B nodes under consideration at the depth, but only W nodes will be selected. Okay, let's see the algorithm. So here start and goal nodes and local variables, and output is SR node. So the first it will be initialized with the root node and found equal to false. It will check first the current node is the goal node, then it is found will be true, otherwise find successors of nodes, compute their estimated cost and store them in the open list. Next, found equal to false and further expansion is possible. Then open list based on the estimated cost. Top W elements from open list will be taken and it will be carried to the same will be repeated. If node in the open will be the, if it is the goal node, then it will stop traversing. If it is not, then again it will goes to the next level. Let's see the example. So this is the root node, and here the W equal to 2. So in each level, look at the first level. Here it is the root node contains the 3 successors. Out of these 3 successors, it is taken as 2 best nodes. Let's see the third one. 1, 2, 3, 4, 5, 6 successors. 6 nodes are there. Out of these 6 successors, it is taken 2 because W equal to 2. So this process will continue till goal state is found or not able to proceed further. If it is the solution is not exist, then it will terminate the algorithm after reaching the terminal nodes. Let's see the one example. So here this is the graph. Here A is the start node and J is the goal node. Okay, so the first A will be taken. For example, W equal to 2. In this case, A equal to 10. Okay, A will be explored, B and F are the successors to A. A will be matched with the goal node. It is not a goal node. Then it will be explored, B and F. So again, it will take 2 best nodes, and A having only 2 nodes, so the 2 will be taken. So 8 and 6. So it will be explore B. B having C and D. Next, F contains G, H. Now the C having 5 and D 7, G 5 and H 3. in this third level, it will take 2 best nodes because W is 2. The width of the node is 2. That's why it will select only 2 best nodes. One is H, another one is C, because the C and G having the same heuristic value. So it will take any one of the values. So I am taking C and H. Next, H will be explored. H value will be I, and F already examined, so it won't take H, F value. Next, C will be explored. D already explored, so C is E. Okay, so here also we are having only 2 nodes, so 2 will be explored from E to J, I to J. Then it will calculate the cost from A to B, B to C, C to E, E to J. If it is the least cost, then it will be the optimal solution. Then here also it will calculate the cost A to F, F to H, H to I to J. Which one is having the least cost? It will take that as the optimal path. So A to B 6, 6 plus 3 9, 9 plus 5 14, 14 plus 5 19 is the cost here. A to F 3, 3 plus 7 10, 10 plus 2 12, 12 plus 3 15, 15 is the cost. So here the solution path is A to F, F to H, H to I to J is the one of the path. Okay, this is the optimal path because the least cost will be the optimal solution. Next, best first search. So the next algorithm is best first search. It is a way of combining the advantages of depth first and breadth first search. So in best first search process, we select the most promising of the nodes we have generated so far. In this, we have taken W number of best nodes, but in best first search, we will take only one of the node. This is done by applying an appropriate heuristic function, which is having the smallest value will be carried towards the goal state. In some cases, we have so many options to solve, but only any one of them must be solved. So here in AI, this can be represented as a R graph. Next, to implement such a graph search procedure, we'll have open and closed. Open contains the exploring nodes. Closed contains the already visited or examined nodes. This is the algorithm, the same content. So method is open list with the root node, closed is empty, open is not empty, and found is false. Then first it will check open is the goal, found equal to true, otherwise remove the first node from the open and move it to closed, add its successors to open, sort open based on a heuristic function, estimating the cost to reach the goal. If found is true, then yes, otherwise no. This process will be repeated until it reaches the goal. Let's look at this example. Initially, A is the root node. A is explored, B, C, D. Next, B having 3, C having 5, D equal to 1. So, out of these 3 values, D is having least value, so it will be explored. So, after that, E, F. If E contains a 4, F having 6. So, 3, 5, 4, 6. Which one is having a lowest value? B. So, again, B will be explored. G, 6, H, 5. Again, it will be compared 6, 5, 4, 6. So, which one is having lowest value? 4. Then 4 will be explored. I, 2, J, 1. So, J is the goal node. A is the start node and J is the goal node. So, the optimal path is A, D, E, J. Look at here. A0. Closed list is empty. Next, in the step 2, A is explored, B3, C5, D1. Next, D will be explored. Okay, so in open list, it contains B, C, E, F. A, D is in the closed list because it already explored. Now, B contains the smallest value that will be explored, and C5, E4, F6, G6, H5. Already examined nodes are A, D, B. Next, in the last step, it contains C5, F6, G6, H5, I2, J1. Next, A, D, B, E, J is the optimal solution. So, in today's session, we have seen the heuristic search algorithms. In that, branch and bound. So, it will calculate the cumulative value from start node to current node. Which one is having the least value? It will take that path and that branch, and it will leads to the solution. The second one is hill climbing algorithm. Whatever least value is there, the current node, it will explore only that current node. After that, it will check the successor's least value and it will go to the till goal will be found. If it is not there, then it will be found as the there is no solution. Okay, in hill climbing, it contains the three problems. One is local maxima, ridge, and plateau or flat area. Next, in the third one is beam search. So there is a W number of nodes will be carried to reach the goal state. In the fourth one, best first search. So only one best node will be carried to the goal state. This is the summary of today's session. In next class, we'll see the A star algorithm and iterative deepening A star algorithm, and one more is constraint satisfaction. Thank you.